Okay, so hi everyone, I'm Raluca and I do protocol architecture at NIL Foundation. And today I will be talking about mechanisms for unlocking idle blob space. So the talk is structured into broad parts. First, we will go over how we use blob space today, specifically Ethereum blob space, and also how we can use it more efficiently in the future. So we start with a few specifications, and we look at three broad numbers. First is the number of bytes per blob. Each blob carries around 131,072 bytes, or exactly not around. And this blob is made of 32-byte field elements. And then we look at the number of blobs per transaction. So one Ethereum transaction, specifically EIP 4844 transaction, can carry between 1 and some limit number of blobs. In this case, we have an example of 2 blobs per transaction. And the third number we care about is the number of blobs per block. So one block can carry between 0 and the same limit number of blobs. And it can contain multiple transactions that carry blob, and they have to sum up to the limit. So in this case, we have one transaction that has 4 blobs and one that has 2 blobs. And this target, this limit, as well as the target number of blobs, which is lower than the limit, are set per fork. Currently, we are at 6 target blobs per block and 9 limit maximum number of blobs per block as of Pectra. Okay, if we look at the way we use blobs right now, or at their number, we can look at this blob scan graph. And since Spectra, we see there was an increase in the number of blobs we use daily. And since Spectra, we use around 27,000 blobs per day. And when we look at the number of bytes, the distribution is the same because all blobs have the same size. We score around 3 gigabytes of bytes per day. However, what these graphs don't show us is all of the blob space that was actually provisioned, but we did not use. So let's start looking at that. First, we look at the number of at how we use blobs. So in order to do that and see the blobs that we have not used, I looked at the last 15 days of Danksharding data and the first 15 days of Pectra. And remember that the target blobs per block for Danksharding was 3, and for Pectra it is 6. Why do I use target? Is because target is where we reach market equilibrium, so the supply that Ethereum provides meets the demand of how much blob space rollups actually need. And the total provisioned blob space, so how many blobs we could have used in this time up to the target, of course there's more up to the limit, is around 300 for Danksharding and double of that for Pectra. But now the interesting numbers. So first, the average blobs per block, because remember some blocks can have multiple, more blobs, some other can have less. But for Danksharding, this number was very close to the target, meaning there was very little space to actually scale. For Pectra, however, this number is quite a while from the target, meaning we still have some space to scale the rollups. And if you look at the percentage of the number of blobs we don't use, for Danksharding this number is insignificant, whereas for Pectra we still don't use 40% of the blobs. And remember, this is just for the first 50 days of Pectra. Things might have changed a bit since then. And in terms of TPS, this means less than 1 transaction for Danksharding, which means we just couldn't scale Danksharding further, or like the data we put to Ethereum. Up to the target. Again, we could actually scale up to the limit more. And for Pectra, this number is 143, which means that on top of the current 260 or so TPS that rollups collectively achieve today, we still have space for 143 more. Okay, now let's look at where these blobs that we don't use are. So here we have a blank canvas, and this was for Danksharding. We have 100 blocks. And the gray area is all the target, surface we could have used. And everything else up until 6 blobs per block is just the limit. And if you look at the Danksharding data, it looks something like this. So we see 2 things. First, there's quite some blocks that have excess blobs, the ones in orange, so they're over target. And there are also some blocks that use no blobs for different reasons. But this already shows that maybe we could do something with the orange part and move it to the gray area if we know how to do it more efficiently. If we look at Pectra, things are even a bit more relaxed. We have a whole lot more of gray area. We still have a lot of space. And also just a few blocks go over target. Okay. Now we can look at the number of bytes we actually use from blobs. And if you look at this blob, it only uses around 150 bytes of data. Everything else is zero padding up to the 131,000 bytes per blob. And this means a 99.88% waste rate. And these bytes are actually paid for, and we don't use them for anything. There was a study that looked at the first 6 months of Diugan data and looked to see exactly how much data we put into blobs on average per rollup. And they found between 0.14% and 99.99% of data that put into blob was reaching the blob size. If we flip this number, though, the waste rate is between 0.01 and 99.86%. Meaning in some cases, we waste almost the entire blob. And this points to the following conclusion, that blobs are not a one-size-fits-all solution. So some rollups benefit more than others. Particularly low data throughput rollups can struggle with this because they don't have enough data for how much a blob requires. And they're left with one of two options. They either submit partially empty blobs, and they just pay for 0 bytes, or they delay their DA submission until they collect enough data to actually make good use of a full blob. However, this gives bad UX. Okay. And if you look at the same data set from the first 15 days of Diugan and the last 100, what was it? The last 15 days of Diugan and the first 15 days of Spectra, we waste around 5 billion bytes for each, which in terms of transactions is around 30 million transactions. And that's around 2 million transactions per day for each fork. So this is the transactions that, instead of being used for actual meaningful data, it's just 0 bytes. And I forgot to mention, but for transaction, I take 180 bytes for transaction. Of course, sometimes it's more or less, depending also on the data compression algorithms. But yeah. The most interesting part is, though, that this is actually around 22 to 23 TPS that we don't fit in data because we use 0 bytes instead. And this is actually the TPS, or like very close to the TPS of the second largest rollup today, which means that we could actually fit another second largest rollup today for free. We could fit all of its data for free if we make use of all the 0 bytes spread all across the blobs. Okay, so also let's look at how this waste is distributed. So we had this figure with the first 100 blocks of Spectra, and this is where waste is situated. You can see there right in the middle. I don't know how to point. I think like that. Anyways, so we could just avoid even reaching, overshooting the target because those bytes are 0 bytes. Okay, so going back to the title of Unlocking Idle Blob Space, we can now have an idea of what idle blob space even means. And I will use the words of a very famous person who said that it is not only idle the byte which does nothing, but it is idle the blob which might be better employed. So if we look at these bytes, they do nothing. They just are 0. They carry no meaningful data. And if you look at these blobs, they could have been better employed by storing these extra blobs from from a previous block. Of course, this matters more in high congestion periods. Okay, but how do we actually unlock this idle blob space? And I will go over a couple of approaches. There's various prototypes and research going on, so this is partly a systematization of knowledge of them. And these approaches deal with the data that we put into the blobs, the blob itself, the block, or the transaction, the EIP4844 transaction. So let's go over a couple of examples. First, we could adjust the data that we put into the blobs. If we take this example, is how some rollups actually define their batch. They define a batch that they post to Ethereum in terms of the blob size. So they stop adding data to batches when they reach the blob limit. And there is one example that I looked at. And out of 4 blobs that they used, they wasted 24,000 bytes across all 4 blobs because of this method. And this could have actually fit them 131 more transactions. But instead, they used 0 bytes for all of those. And the solution to that, or one alternative approach, would be to stream the data and not stop forming the batch when you hit the blob size, and then just use that extra space to fit more transactions. Okay. Another approach is to adjust the blob and for example, doing dynamic blobs. Remember that one blob has 131,000-ish bytes, but we could maybe think of making it smaller or larger depending on the rollup's actual needs. So in this case, the blob size would become equal to the data size-ish because we still will use some padding. For example, if we have 88 bytes of rollup data, we fit it over 32-byte field elements, just as we do now. So here's our data. And we also have some extra 8 bytes of padding just to fill that last field element to the end. In this case, we would define the blob. We could define the blob space per block as total bytes and no longer think in terms of blob count per block. And also, the blob would have field element granularity, so it would be a multiplier of 32 for each for the blob size. The one good part of this is that we don't affect the execution cost in any way because the service having the opportunity to post data to Ethereum is still paid in full, but data is paid proportionally to the consumption rate. And there are maybe some challenges with how to match this approach with future Ethereum upgrades, such as sampling. And there are some proposals that look into dynamic blobs, and I linked it here. And their proposal is to simply have multiple sample sizes to make sure that we have sufficient replication for all different blob sizes. Okay. One other approach has to do also with the blob, but it's actually not adjusting the blob size, but rather the contents that go into the blob. And this is blob sharing. It's quite straightforward. We have a couple of different rollups. These rollups have different data shares of different sizes that come in at different intervals. And there is some blob sharing service that collects all of these data shares. It applies some aggregation algorithm over them. For example, the largest comes first, or based on some whatever priority definitions. And then it applies some transaction submission strategy to decide when to submit the transaction and how many blobs to fit in the transaction. So finally, they get one transaction that may look like this. And they send this to a shared contract from where all of the other rollup contracts can read the relevant data for them. One question that we could ask here is who would actually operate this service? And I propose two broad categories. We could also think of L1, but we're trying to keep it realistic. So it could be the rollups themselves, who could sign some or join some form of agreement that they will collect, rotate and each take over these responsibilities of collecting the data, aggregating it, and posting it together. Or it could be some third-party service. And these are already some prototypes at different stages of development that you can look into more if you want, but they all follow the same architecture. And also because they are thought of as third-party services, they also discuss some incentives for the aggregator. So the rollups would also pay some commission to them. And there is this blob sharing study that I also mentioned earlier that looked at the first 6 months of the Danksharding data. And they simulate blob sharing, and they noticed that the whole data has a slightly increased because of the added overhead. In order to identify your own data share within a shared blob, you would have to also add some identifier for the rollup. But they naturally noticed that there was a decrease in the number of blobs, which is good for all rollups because there's more of them available, more of the blobs available. So at NIL, we work on ZK sharding, which is a validity rollup architecture where the data and execution are sharded. And we have, for shards, we have two state update options. We either update their state individually or in aggregate. And so we also either post data individually for them or in aggregate. And blob sharing was very helpful for us in this case because it actually makes things more efficient. So here we have a couple of 3 shard chains, which do some cross-shard communications between them. And we decided to go for blob sharing. It's not the same we don't have multiple rollups, but we do have multiple chains which can aggregate their data together. So we have a synchronization layer between the shards and Ethereum. And there, as part of the synchronization layer, we have an aggregator which collects data from all the shards, and then it sends them. So it applies some batch streaming to like data streaming and creates the blobs, and then sends them to the batch committer, who sends them to Ethereum. Then at the same time, it also sends this data to the prover. We generate a validity proof here. There's a big question on how does blob sharing work with proof of equivalence. For us, it's quite straightforward because we run a single, like a unified proof system. Whereas if you have multiple rollups that have heterogeneous proof systems, things might not be as easy. And then we also send the proof with the new state to Ethereum. Okay, the last mechanism we're going through has to do with the transaction and the block. And this is particularly for high congestion intervals. So once the blob fee actually gets a bit higher, because right now they're basically, blobs are kind of a gift from Ethereum. So this mechanism is called target-based block building. And the idea is quite simple, to just aim to have a target number of blobs for each block. And this could work in a first-in, fitting, first-out method. So we look at the transactions, and when building the block, we just take the first one and then the next one that fits in, and so on. But this means that we also skip over some transactions, so those would actually incur some delay. One way to make sure that we don't go into that is to lower the blob count per transaction. So in this example from the first 100 days of Pectra, we could actually not form a block that only has 6 or target blobs per block, because the transactions look like that, like 5 plus 4. So we had to wait a bit until we get that one blob transaction to make a 6 blob transaction one. But if we lower the blob count, then especially if all transactions have 1 blob per block, then there's almost no delay because everything comes in as it's submitted. So, and there is some research that already hints at the fact that rollups do respond to market conditions, short and long term, and they adjust their blob submission strategy and like transaction submission strategy. So it's not an incredible thing to ask them for. And also there is another preliminary research that shows that frequent and smaller transactions actually have lower delay. So this lower blob count per transaction might be a good idea. And this also helps us actually stick to the provision target blobs and not go into fee increasing territory, meaning we don't go over target unless really needed. And this, however, has a very bad downside for high data throughput rollups, because they would have to pay execution costs for each DA transaction, which is probably inconvenient. But yeah, that was the last mechanism. And just to wrap it up, I want to say, so we have a couple of different options for scaling DA further. Do what we've been doing so far, which means increasing the blob count, and wait for sampling so that we actually don't run into bandwidth limitations. Or we could also minimize waste, which would be the best of both worlds. And some possible next steps on this research area is to analyze the actual cost implications of these different waste prevention mechanisms, because I've mostly talked about storage. Like I've talked about waste in terms of storage, but also we could see the actual cost implications of it. Some of the studies that I've cited do that. Also get some incentive alignment between all actors, from block builders to rollups to Ethereum R&D and third-party services, because I don't think they're fully all on the same page with this kind of mechanisms. And also think about how these mechanisms fit with future upgrades. Yeah, so this was me. I guess I'm allergic to waste, and that's why I made this presentation. But basically, but thankfully not literally, because we've seen there's quite a lot of wasted blob space. Yeah, I appreciate your attention, and I'm happy to take questions.
Thank you so much, Raluca. That was great. So we are moving into Q&A, and we already have a few questions. But if you haven't put up your question and have one scan the QR code and put it there or upvote other questions. So first question, and I'm selecting it for answering. In ZK sharding, how exactly does the synchronization layer work? Is it a centralized service?
It is thought as a decentralized service, but it starts as a centralized service, yes. But later on, so it is a single entity right now, which interacts with all the shards and with the prover network. But then later on, these different components, so even the aggregator or the proposer, could be further decentralized in standard rollup fashion.
Okay. So second question. In the case of blob sharing, what are the exact liveness and security assumptions with a shared blob service? What are the effects on settlement?
Right. So, for example, one issue that could be is that the blob sharing service does not actually end up posting the data, so we never get to finalize our the new rollup state on Ethereum. So there are two mitigation mechanisms at least for that. First, you can actually have some staking of the blob sharing service to make sure that cryptoeconomically they are incentivized not to be malicious. But also you can have some form of timeout that if your data is not posted by a certain amount, like a certain block limit, you would post the data yourself.
Makes sense. Oh, a new question just arrived. So, are you aware of any rollup teams exploring blob sharing? Are there any blockers stopping us from implementing blob sharing independent of the L2 protocol changes today?
So I'm not sure I got the second part of the question, but no, I'm not.
Should I reread it or?
Yeah.
It's a bit hard to read from the stage, but okay. So, are you aware of any rollup teams exploring blob sharing? Are there any blockers stopping us from implementing blob sharing independent of the L2 protocol changes today?
Independent of the L2 protocol. Okay, cool. No, there is nothing stopping us other than it's kind of a separate research direction that can complement Danksharding. It's not that we cannot do it. It's just it also requires some research to actually understand how we do it. So, for example, if we want to do proof equivalence, which is showing that the data we actually post to blobs is the same data that we prove, it's a bit more difficult to have two different rollups agree on how to do that, or actually even like decide who does it. Is the blob sharing service responsible for that part of the process, or are the rollups themselves? And it's just starting sort of the conversation and trying to realize how feasible it is and for what type of rollup architectures it fits and whatnot. And to answer the first part of the question, I am not aware of rollups that utilize blob sharing service, but I know that there's one service that is live, so maybe they will start looking into it.